Hello. Hello.
Oh, YanKeen, yes, right. How come? Okay, right. So sorry, I didn't notice that you're in early. Can you hear me loud and?
Yeah. I can.
Right. Did you wait long? Sorry.
Oh no, just like 1 minute.
Oh, right. Okay. Right. Sorry. Yeah. Usually I'm notified. The Jamboard.
Yeah, I'll create one.
Because last week's is already full, right? Yeah, it's almost already full, right? Okay.
Give me a second.
Sure. When you're done, you give me some updates, yeah?
Yeah. Right, I am sharing the Jamboard with you now. Okay, I shared it.
All right, got it. Okay.
So in the way of updates, Friday we had chem, and we finished up the carboxylic tutorial.
Okay, cool. Right.
Our teacher wants to speak through some of the nitrogen tutorials next week. So she said she'll probably go through a lot of it very quickly. So I need to work on that. And physics. There's been no physics since Thursday. So we'll probably continue quantum next week.
Right. Yeah. Okay. Last time you said is at what do you call it? The
emission line spectra.
Yeah. Okay.
I think there's still a few questions on emission line spectra left that he hasn't gone through. So he probably do that, and like I think the next part of quantum as well. As for what I'm doing, like the weekend, it's mostly like catching up the lectures like today. So some of the nitrogen compound stuff. I went through the SLS for that, and some of the quantum as well. Because like, well, physics I was very unprepared for quantum, but I went through some of the emission line spectra stuff, physics, and then I think I made it up to. What's it called? Let me just check. I got some quite. I know I got quite a ways into chem. I haven't hit amino acids yet, but I'm pretty sure amino acids is the last lecture anyways. So that's where I'm at. I'm gonna be honest, I should have put more time to like actually write stuff down, like tutorial wise. But I'm very behind on lectures, I think.
Right.
Cause like chem bond by Wednesday we'll be going through electrochemistry again, which is a chapter ahead of where I'm at now for SLS. So I have to buck up, I guess.
Right. No worries on that. That's what we expect, right? Because exam, right? Past exam. That's what happened. But so our situation is currently not surprising, and you may say that it's bad, but don't be afraid. I just want to clarify something. You're saying that the quantum, the emission and absorption spectra, you're saying that your teacher has a few questions left. Does that mean that it's already in the tutorial?
Yeah, it's in the tutorial. I mean,
So,
obviously, it's the tutorial.
And just now you were saying that you are still catching up on the lecture.
Yeah.
Okay, so a little bit of correction. Maybe I should have said this earlier, yeah. But I know we're behind. So there are two ways to catch up, right? We catch up while everybody is, let's just say everybody. That's not really true, you know. Most people are behind at this point, right? Because nobody can prepare for, you know, exam and study the current topic at the same time. Well, nobody can. You must understand this first. It's just usually not human possible throughout 4 subjects, maybe 4, maybe 5. I don't know, right? Okay, so that's not possible. So what I should have said to you is that in quantum, the topics are actually fractured. They are not continuous in a way. For example, the superposition. They are quite continuous in superposition, or in the first few chapters of GC1, they are very continuous, so to speak, like the forces, the moments. So the quantum are going to be fractured until the end. So the most continuous you will get is from actually there isn't much. Like they have some connection, but they are very fractured. I should have said to you that
they're separate.
They are almost separate. They are almost separate, right? So
okay.
So I should have said you, okay, we should have catch up using the I feel more appropriate method, as in we just jump to the lecture after this lecture, like we jump ahead, and we're going to leave these things behind for now, because catching up this way means you're gonna play catch up for a long time, right? So I should have said that. My apologies. I didn't realize that. So, but what you have done is fine. What you have done is fine. Because I didn't say so. That's normally what people will do. We just go. But today, for example, let's say that means you haven't even had any questions on the tutorial, right? Because the tutorial you haven't done. Correct.
Yeah, except for the parts that my teacher already went through. No, like nothing I have for myself. Because
then
a lot of questions I had, I just looked at my notes that I already answered them.
Correct. I understand. So I'm not saying that these chapters are not important. I'm not saying that. I'm saying that we can catch up later, because again, the chapters are fractured. So if you have the next chapter on quantum, we should jump to that immediately, and therefore you are straight away at the pace of the class again.
Okay.
Right.
The next
so
one is
that's for physics. Right. Now that's thing for physics. Just a minute. So for math, right? Yeah. So math is not fractured. Math is like a continuous thing from start to the end. So math is a bit strange. I just want to understand, because you said that you're already at binomial and normal distribution.
Actually, we're at what's called sampling and estimation theory.
My goodness.
Yeah, okay. But we haven't even started binomial tutorial yet. So
we
so lecture wise we're here. But tutorial wise we are at.
So I'll go fast. I'll go quick. I'll ask a very quick question. Because we're currently playing catching up in 3 or more subjects. Maybe your econs are even catching up, right?
I don't have econs with history.
Sorry, history. Right. But history I'll leave to you. I trust you with history and GP, right? So three subjects to catch up. We probably should focus on 2 only first. So the other one, you'll be playing catch up by yourself for a while. For a while means for 1 week, right? Okay. So which one will you choose for us to focus?
Probably gonna be physics and chem. Because math, at least I have a strong base for my lectures. I just need one tutorial. Physics and chem, I need to get the because math lectures are the only ones that are built into the timetable. Physics and chem I have to do it myself outside of timetable.
Okay, right. So I will trust you with math one. Sacrifices on math are not good in a sense, because it's not fractured. They are one continuous thing, and if it is continuously studied, it's not very difficult. I promise you this. Like the chapters that you are doing right now, even though things are seen a bit abstract, but after you do it, it's not as easy. It's not as difficult as the PNC. I did promise you that. Correct. It's not as confusing, and it will continue to do so even until the end, right? So we're leaving math behind a little bit for now, but if you sense, you're a bit off, you gotta tell me. Understand?
Okay.
Right. So that's just okay. So now for physics and chem today, lah.
Sorry. Speaking of math,
Yeah.
I thought that I do I want to diverge it now because I got back my CAP. So we will talk about that later.
70 out of 25 looks very nice.
Yeah.
This was the exam that happened just now.
Yeah, the one that I had to sacrifice time for.
Right. Very good, right? I don't want to talk about it too much just because we're catching up, but I want you to take picture. I really want. Then I'll take a look, and when the time is right, then we'll discuss.
Yeah, back
Okay.
to physics and chem.
All right. Now send me immediately after today. Okay. Understand?
Yeah.
Right. And you still, you still have to find, because you only sending me chem from last time.
Okay.
Right. Okay.
I sent you math as well, right? Didn't I?
Did you? Okay, we'll check later. Whatever.
Yeah.
Right. So for today, let's focus again on phys and chem. Your choice first. You want to ask question or you want to catch up the lectures immediately? Either one, we should do all. Right. Let's go.
But I can't ask questions. I don't think. But I think you have to have.
Okay. Then shall we catch up on physics? No. Shall we get ahead on physics lecture? So the lecture after absorption and emission.
So that'll be X-ray.
Right. Okay. Show me first. So you haven't learned this lecture. Lecture haven't started on, correct?
Yeah, basically, yeah.
Okay. Zoom in, and then I will help you understand the upcoming lecture. Always the same thing, right? Okay. Prepare your question marks. Even if I explain to you, you will still have question mark, and that's what the lecture is. That's an ideal way to study lecture lah. You come in prepared with your question, not prepared with your answer. Right. Okay. So blah, 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 blah. There's only one thing I want to say here. X-ray is after UV, so they are lower in wavelength. Now, does that make sense?
Yeah.
Smaller wavelength, more energetic lah. E equals to HF.
More high frequency. Yeah.
Correct. You still need the equals to HF, by the way lah, in all quantum lah. Yeah, you will need that. Okay. So go move down. Blah, blah, blah. Okay, let's go. The left page first. All right. Okay. Now look at this production, because the production will always be important. You can either memorize it or you can either understand it. This is the way I started the previous quantum, the photoelectric effect. I want you to understand what was happening. Remember I was saying this is a gap, then suddenly there's a current, that kind of thing. Okay. Yeah. Now this is how X-ray was kind of discovered the first time. You see that electrons going out of the cathodes.
Yeah.
Yeah. Now those electrons are clearly not in a wire, right? Because they're usually flowing in a wire. And those electrons are in a vacuum. Same thing. Okay. So those electrons are really flying out for reasons. The reason is explained later, but reasons. Okay.
Is this not like same as photoelectric effect?
However, photoelectric effect, you hit the cathode with light, right? Photon, right? And then the photon get absorbed and then kena text a bit, right? Remember the work function of the metal. Then the electron shoot out, and then you suddenly have a complete circuit lah. So the electron flying out is completing the circuit. Here I can say this is the reverse. Yeah. So the electron flying out is not because of any photon input. It's because of the cathode is being heated. You just see that is an electron emission by heating. For some reason, if you hit the cathode, it will eject electrons. No other explanation given. However, it's not very difficult to understand, because remember that every atom inside a material, whatever that is, does vibrate, a solid, right? Higher temperature, higher vibration. Those higher vibration do tend to knock electron out of the orbit, meaning to say it gives electron enough Ke to escape. It's as simple as that. So higher temperature, and we're talking about very high temperature, by the way. We are talking about not just a temperature. They don't care about that temperature. They just care that the electron, okay? Right? Now it is being directed from the cathode to anode. It's implied lah. If you have cathode, you have anode. It's just implied. Okay, it's just implied. Okay, remember anode, the mean, oh, sorry. Or rather, do you remember from O level? The meaning of anode should be like this. It's where the anions go.
Yeah, so it's testing positive charge.
It receives the negative charge. So as weird as it is, the electron is currently exiting and entering a negative. They don't explain this. They don't explain this. They just, okay, you're just gonna accept, right? You're just gonna accept that. So the important part is not all this. The important part is that when the electron hits a target, that's where it is important for our syllabus. The rest are important when you try to do the experiment. You won't be doing the experiment. These are dangerous experiments, like really dangerous. Right? So the electron is hitting a target, and the target, interestingly, is also usually a metal. They don't say, but it is usually a metal.
But why does it have to be a metal?
Right, because for some reason, no, actually, I don't understand the reason enough, but it is usually a metal. It doesn't have to be a metal. It doesn't have to be, but it is usually a metal. No, actually, it has to be a metal, but they also don't care in the syllabus. What they say is this: the electron, which is super fast, hits the target. The target, well, does not melt. First thing first, the target should have melted, because this is a lot of electron flying at very high speed, hitting the target, giving the target a lot of heat, which is why you see the cooling fin. Keeping it simple, right? Okay. Now, he's saying to you, that's so weird. When I hit the target, the electron basically stops. The electron does not bounce. The electron does get absorbed, but lo and behold, a strange ray exits the target. Those are the X-rays. So think about this for a while. This is the exact reverse of photoelectric effect. Photoelectric is you hit something with photon, the guy ejects electron. This guy, you hit something with electron, the guy ejects photon.
But isn't photon like?
Isn't
I thought photon was like light, not just electromagnetic radiation.
You mean visible light?
Yeah, I thought photons were.
Yeah, wrong in the sense that that's not how they define the term. That means the general agreement with everybody is photon works for visible light and invisible light. They are still photons. They are still electromagnetic radiation. If you don't know this, well, that's very important. It's very confusing if you think about it that way. Right? So when I say X-rays are photons, I am correct in terms of the definition. When I say X-rays will have energy equals to HF, that's correct. Okay.
Okay.
To be very clear, if you hit the target with lower speed electron, it will probably eject other photons which are lower energy. Probably. We are talking about a high enough speed of electron hitting a metal. The metal doesn't melt. The metal somehow ejects X-ray. Voila. Okay. Right. And that's a very basic, not even complete explanation of the real experiment. Right. So done. Okay. Done. At least you know that all this is happening and all this happens in vacuum. Okay. Yeah. Any other question for this page? Let me show me the bottom part. Yeah. Oh yeah. I forgot. The emitted electron is accelerated even. Yeah. Sorry. The electron does not need to start with a high speed. That it will be super accelerated. Meaning to say you just have a very high speed. Yeah. Which surprisingly doesn't melt. Yeah. See, another heavy metal of high melting point. It explains why. Right, because you need a high-speed electron. You do need that. And see, I just told you photon in this case actually like a super high energy photon. Super high energy. Okay, so done. Right. Now, put question marks if you have, and let's move on.
So
Now,
this just happens.
Yeah, this happens for some reason. They will explain. They explain the target part. They don't explain the electron emission part. They just explain the part where how come the electron is being absorbed by the target, and then suddenly, so to speak, the target emits X-ray. They are interested in that, and they want you to understand that, and they will test that, so to speak. Yeah. Okay.
All right.
So upcoming to the next page. Please take a look at the next page. So the next page summarizes every X-ray question in exam. That means they feel this is the important thing. I can feel differently because when I read the X-ray history, I feel that a lot of things are very interesting. They don't show all of them here. They really don't. Like I was wondering, the history is much more interesting than just this graph. But they decided for this syllabus, this is the thing to at least understand. And maybe next time when you have time, we'll go and read the history. Quite fascinating. Okay.
All right.
So I apologize for the pared down story. This is totally pared down. Okay. Now, the graph needs to be understood. Look. If you understand this graph, you basically understand 80% of the X-ray chapter. It's not a long chapter. So you look at this graph, quickly determine what you don't understand, and then I'll explain immediately. Please quickly, give you 1 minute.
Just look at the graph.
Yeah, and look at try to understand the graph. You're a physics and math student, what the heck? What is this? What is that? What is this? What is that? Oh, this, and then then we'll talk about it.
I mean, obviously the slide, and suddenly going back down.
Yeah, there's that.
Because it looks like it's meant to go meant to be like that straight down like
you
that.
can say that. I'm pretty much sure that was the case. So there are two spikes in the otherwise gentle spectrum, what they call the continuous spectrum, is it? So you're focusing on the third and the second guy, the third and the first guy. You haven't focused your eye on the third and first, not the second one, right? So why that means they draw your attention, right? What is this lambda minimum, right? What is that?
So yeah, minimum.
Why is it minimum that is interesting? Why not maximum, for example, right?
Okay. Guess I'm not sure.
Right. So that part I don't like. So I'll explain it immediately. I hope you will get it. Right. So the lambda minimum implies minimum energy or maximum energy or whatever, not necessarily both.
Minimum.
You nonsense.
The minimum lambda to get X-ray?
No. The minimum, well, you're saying that you're basically with that, you're probably implying that the longer wavelength are easier to get. Basically, you're implying that.
Longer wavelength easier to really?
That means let's say the lambda minimum is 35, let's say, according to this graph.
Yeah.
So you're implying that the lambda 40 is harder to get. Sorry, is it easier or harder? I don't know.
Well, I'm not sure what relative intensity is. So I'm not sure if it's easier or harder.
Well, if I scratch the relative word, just intensity, does it help?
I mean, like intensity as in light.
I mean, we are talking about light, right? You're a physics student. You should not think of light as visible light. It's a problem because we come from we are commoners lah. We're normal people ma. We say light, visible light lah. But in physics, light is both visible and invisible.
Okay.
When they say photon, it's light. When they say light, it's electromagnetic spectrum. Our thinking in physics is different from our thinking as a normal people. In normal people, we don't say things like, it's invisible light. What the heck, right? But in physics, we can say that. So even though it's invisible, it still has intensity.
Okay.
Even though your eyes cannot, right? Even though your eyes cannot see.
So intensity is determined. what does intensity have to do with it being easier or harder?
I don't know. So I go back to
In-
my question. Why lambda minimum? Why not lambda maximum? And then I was asking you another question. Lambda minimum is minimum energy or maximum energy? You choose minimum energy.
Ah, maximum. What am I talking
Very
about?
good. Yes. Now you're talking sense. Why?
Because HC over lambda equals to the energy of
Correct.
the
Because
photon.
HF, right? Because HF, yeah, lower wavelength, higher frequency, automatically. So you write it down, even though you might not know the main point, but you know why we worry about lambda minimum, because that's the maximum energy. And turns out that X-rays are high energy, and the highest energy that you can get kind of determines the limit of the X-ray, how far you can push it. Okay. Now the spike wise, so there's a continuous spectrum, right? The spike, that means the spike in intensity, basically. So you have more intensity, right? Which basically means you have more photon there. Keeping it simple, you have more photon on the K alpha spike and the K beta spike, and why something like that. Because most targets, the metal that you hit with the electron, right? Most target produces this kind of wavelength. Just a different spike here and there, but you will have the spike. Okay. So you may say that, yes, you're saying?
Why does intensity mean more photon? Doesn't that mean, isn't intensity like?
My goodness, you have problem from the start. I have to explain intensity. So I was telling you that the E equals to HF carries over from start to end, right?
Yeah.
So that's continuous. Intensity, same thing, from start to end. That means you didn't understand intensity when they talk about it in photoelectric. I didn't talk about it at first. That's a problem. That is the key to understanding what photoelectric is. So good question. Good question. So intensity in normal people's thinking, which is again us, right? We're just starting to discuss physics, but we are a commoner for a long time. When we talk about intensity, we usually meant brightness law. Wow, so bright, so intense. That's a normal English usage of the word. Isn't that correct even in physics? When it is more intense, it is more bright, it is more photons striking your eye, in some sense, right? How else can you see it as bright? More photon, right? If it is dark, then very little photon, very few photons. Right? Okay. Makes sense?
So intensity determines the number of photons
per area. That's what you're missing in terms of accuracy. It's number of photon per number of energy represented by the number of photons, because each photon is a small pack of energy, right? Correct? So when you say number of photon, it automatically is number of energy. Automatically, because every photon is energy. Every photon is HF. N number of photon, and HF is the total energy. Correct?
NHF is the total energy.
See, is there? NHF, see, big NHF. HF is the energy per photon. Right? Because lights are just energy. That's what they're implying here. It has no mass, but it's pure energy.
HF
right?
is of one photon.
One photon. So why are we worried about N? Yeah, because there are a lot of photons, right? So NHF is the total energy. You can say that, right?
Oh, I thought it was. Okay, I thought NHF was the energy of like all photons.
So even though you see this quite a lot, don't think about it as a formula. I think about it as, of course, there's so many photons, man. Okay. Now, you will be interested in over area and over time. You will be interested on that. In fact, they describe it there to you. See, the total photon, first of all, per area. Because per area is what we usually associate with brightness. it can concentrate the photon, so it'll be more intense at that particular spot. It's basically concentration. It's basically like pressure per area. Okay.
Okay.
This is not the first time you talk about per area. Is what I'm trying to say. It's normal to do that, right? But also per time. So you're looking at the concentration of the photon in an area and with respect to time.
Okay.
So that's intensity in an accurate way. So in a physics way, normal people will just say bright or no bright. Okay. Now, so you go back to the X-ray and he's saying basically, oh, there are more photon in this wavelength. That's the rough way of saying, oh, I just have more photon here in these two things. Why? Because the rest are continuous, something like that. There must be an explanation. Okay. Yeah. Right. So I'm going to explain one first, and then we'll go to one automatically explains two, but two you already know, that's the max energy. Then three is later on. So processes involved in X-ray emission, you go down. Okay, they use the origin. That's not original German word. They use the popular German word back then. Bremsstrahlung. Bremsstrahlung is actually still the name for X-ray in German, right? Right. So you want to concentrate on the word breaking. The breaking describes how the electron is absorbed and, so to speak, outputs photon. Right? Okay. So let's flip because usually there's a picture. Oh, actually there. Okay, here, fine. So the E1 is not equals to HF. The E1 is not HF because that's not a photon. That E is the electron's energy, the kinetic energy of the electron. Okay.
Okay.
That electron, which contains Ke, gets turned because the guy turning it is positive. That's it lah.
Turn?
Yeah, it's because usually electron will just go straight, but suddenly it approaches a positive guy. He gets attracted to the right in this case. He gets turned to the right. And he gets turned to the right, and surprise, surprise, his energy experienced some change. Surprise, surprise. So E1 is bigger than E2. E2 is smaller than E1. This is the part that it should have been easy to imagine.
I guess I can accept that, but
if you can accept that in E1, the velocity, because it's Ke, right? It's Ke, right? The velocity is higher, and in E2 is lower. You can understand why we use the term breaking. The breaking doesn't actually mean it stops. So it's a bit misleading. Normal people say if you brake, you want to stop lah. This is not that kind of braking. This is when you drive a car and you're trying to bend a sharp turn, you will automatically brake. Because if not, you will hit the bend. You will not bend, you will not turn properly. You haven't drive, right? But soon you'll be driving when you're going NS. You're saying?
But and this one because I don't remember some stuff regarding electrons. How come when it's attracted, then it will decrease the velocity?
Right. So the attraction, you can imagine the attraction is to the right of the electron in this case, right?
Yeah.
So that's where the electron has the force to so-called turn right lah. So the electron is like turning right. So imagine that we're driving a high-speed car and we suddenly need to do a rather sharp turn. Frankly speaking, this is a rather sharp turn, considering how fast we're going.
All right.
So if we're going fast and suddenly we have to turn, we realize that I cannot turn with such a fast speed. I have to brake in the driving. So I have to slow down a bit so that I can finish my turn, and then maybe I will accelerate again. That's what drivers do. That's just normal.
So
Right?
is this turn circular motion?
No, it's not a perfect circular motion because you don't even enter tangentially. If you want a perfect circular motion, which is very ideal, your entrance must be tangential to the radius law. This is not tangential, so it's actually a very normal daily life bend where it is not perfect circular. So they don't use circular motion here because it is not perfectly circular. It's still a bend. So you will say, how come a circular motion doesn't reduce its speed? You are right.
Yeah.
In an ideal circular motion, perfect, you don't. Correct?
This is an ideal.
That's not. It's not. It's very actually difficult to achieve a perfect circular motion. Everything must be correct. This is not. This is normal what we experience. We will slow down. We will slow down.
Okay. Yeah, sure. All right.
Right. So if you have a question mark, you put that. But the slowing down means some energy is lost. Correct?
Yeah.
In this microscopic, not even microscopic, this is nano level already. This is already the level of inside an atom. You cannot lose energy as heat. That doesn't make sense. Because heat implies you knock somebody else and you give him your kinetic energy. That's what heat means by conduction, so to speak. So you cannot imagine a conduction happening when the energy is slowing down, and yet the energies must go somewhere. Where does it go? Bypass all explanation. He just say he goes out as a photon. That's the only thing he can do. That's the only explanation is implied here. They don't even say that. It's just implied. Therefore, you produce X-ray. Finish.
How did they know that the energy that came up?
They don't. The energy that came out, which is E1 minus E2, makes sense, right? The energy must go somewhere. So it will, in this case, become photon just because there is no other way to do it. There's no other way but to emit photon. And the emission of the photon is not precise. That's why you have a continuous spectrum, meaning to say you can emit anywhere from the minimum wavelength up to don't know.
Okay.
You can consider the minimum wavelength as the maximum emission. Meaning to say it's when the electron simply almost stops.
But it doesn't completely stop.
Maybe theoretically at one go you can stop. Maybe. That's very rare though, because that means that you hit the positive straight on. That's the only way to stop, to perfectly stop it. Most of the time, the electrons will not completely stop. So you see why in the graph, the relative intensity is very slow. It is very low at the maximum lambda, because it's very rare that the electron will completely stop and simply loses everything. Very rare. That's why.
All right.
But as you go on, it is more likely to lose some of it, So you have the continuous spectrum, and you notice the tail of the spectrum, it doesn't hit zero. You go back to the graph, it doesn't hit zero. It will continue on. I hope that also makes sense. That means you're slowing. That means it slows down very little beyond 90, right?
Slows down very little.
Because it's a big wavelength, which means it's a low energy photon, right?
So
if a low energy photon, you break very little, you slow down very little. Meaning
the photons emitted is emitted is a very low energy.
That means you're breaking very little, means you're kind of not influenced very much by the bend, or you're not bending a lot, something like that.
But why does Actually, no. The lambda here refers to the energy of the
No, the lambda equals to lambda.
lambda here refers to the energy of the photon, right?
Yes, because
Okay.
this is the measure of the photon emitted. You you are not measuring the speed of the electron. You're not. You're not. You can measure the voltage difference. That much is true, but they don't know how to measure electron speed. They can probably measure the wavelength of the X-ray. Perhaps right now they can.
Okay.
Okay. So the continuous spectrum and the lambda minimum and the tail, we have explained basically just using this fancy Bremsstrahlung, the breaking radiation. Just by one diagram, we explain all this, and they expect you to be able to almost vomit this in exam. So either you memorize this, go ahead, or I would prefer that you understand this. That's my preference. That's pretty usual.
But why does this one go up and then go down? Like ignore these two things. Why does it go up like that and then go down?
Simple. Go back to the next page, complete it, right? So that thing, the positive guy. Now draw another. At this point, I will now have to say to you, who do you think is the positive guy?
What do you mean? Positive? I mean,
Yeah. We're talking about something that is happening in the target, right? The electron strikes the target. He say to you that this is actually what's happening according to him. So in the target, that must be the positive guy. Who the heck is this positive guy?
target?
They even say that the target nucleus.
Oh.
The target is consists of atoms, in this case, metallic atoms, right? And the metallic atoms are nucleus, and nucleus are positive and neutral. It's a positive part, Ta-da.
Okay, it's positive.
And draw another nucleus. Right. Now, to be clear, YanKeen, the distance between, let's say the nucleus radius is that small, right? Let's say the distance between this nucleus and the neighboring nucleus is around 10,000 of this radius, around there.
Oh.
Which is like super far. Like they talk about this. They talk about this during the. Do they talk about this to you? They talk about this during the. Did they talk about this? The fact that the atom are mostly empty space, mostly. Like a nucleus is supposed to be very small in what we call an atom. It's super small inside there. So it's a small dense nucleus surrounded by a cloud of electrons. Basically empty space, basically.
All right.
They haven't talked about this.
I mean, not that I remember.
Okay, so after this. Now, my point is, you draw this, of course, that's correct, but the distance is magnified by maybe this like 10 of the radius of nucleus. So you times this by 1,000. My point is, the electron has a lot of space to maneuver in between nucleuses, right? But still, the distance is already in the range of the effect. So most of the electron will still bend to a certain extent. Just say that most electron will, in average, go in between two nucleus. Just say it that way, and therefore will still bend because it is still close enough to feel the effect. Okay. So that answers your question. Why does the continuous spectrum peak? Because there's just an average. There's an average distance where you will very likely go through the nucleus if you're an electron. It's just likely to go through that range. You're not likely to go through very near, and you're not likely to go through very far. You're likely to go through in between. So you're likely to bend a certain way. Therefore, the continuous spectrum has a peak, a gentle peak.
What do you mean go through? Sorry.
Oh dear. Okay, let's go to the Jamboard.
Also, the nucleus is the nucleus is on the metal plate, is it?
The target. Basically, the target is metal. They did say that. And metal to us, normal people are super dense, right? Metal. You're looking at the Jamboard? Yes?
Yeah, I am.
But nanoscopically, they are consisting of atoms, right? They're consisting of atoms, which is a super small nucleus there, with a cloud of electrons, something like that. With a cloud of electrons. Again, basically, yeah, the dots are the nucleus. And the nucleus have their own electron, so electron clouds. You learn this from chemistry, right?
Sure.
Now, I'm going to pretend that the cloud of electron doesn't exist first. I'm just going to pretend, right? Because when the electron hit the electron cloud, there will be no breaking. There will be something else happening, but it's not breaking. You can only break or turn or bend when you're influenced by the positive nucleus. Can you accept that?
All right, I can.
So now the electron coming in, right? So the electron coming in doesn't care about it's not a nice array of electron flying like it's not. They kind of go straight because they're accelerated, right? But let's just say that the electron can sometimes go like that, sometimes go a bit like that, sometimes go a bit like that, sometimes go a bit like that. Okay.
Yeah.
So let's take electron number 1 and observe that as I draw this randomly, I randomly draw a distance kind of slightly in between the nucleus, just randomly. Electron number 4, even though I draw randomly, I end up drawing slightly in the middle. So, okay. So electron 1 and electron 4 will kind of bend around the same way and emit photon around the same energy, something like that, even though I do it kind of randomly. However, electron 2 and 3, by random drawing, kind of arrive a bit closer to the nucleus, a bit closer. So if I keep drawing random stuff, I will soon discover that most of the time, they do go more towards the middle than closer to the nucleus. Your binomial distribution or normal distribution is just distribution. Okay? This doesn't make any sense.
Binomial distribution. So I'm.
Use your mouse. Use your mouse. Use a different color. Draw random straight lines, please. Something like that.
I can't draw very well.
I have a better idea. Right. No, never mind. I'm going to erase the nucleus first, right? You're going to erase those things. So now you're going to draw random lines which represents electron flowing from the cathode. There's the cathode into the metal plate, right? So roughly, please draw.
Like straight lines?
Yeah, straight lines. So go as straight as you can, but with some variations, right? Some variation. Okay, that's one. Okay, we need at least 10 of these, so draw quickly.
Oh. 10.
Yeah, so like quickly draw, right?
Can they like cross each other?
Of course you can. I mean, they are very small, so they are very unlikely to hit each other.
Oops.
No, it's okay, it's okay.
1, 2, 3, 4, 5, 6. 7. 9. 10. Okay, 10 of them.
Okay, so roughly like that. Okay, draw 10 more. Draw 10 more.
What?
Quicker.
10 more?
Okay, quickly. Yeah, 10 more. Boom, 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 boom.
Where? Sorry.
Still around there, because it's still the cathode emitting, still accelerated towards the plate, so this will always be the general direction it's going.
Okay, wait, let me charge my computer. Got it. 10 again. I'm using different color.
No, doesn't matter. Doesn't matter.
2, 3, 4, 5,
Right. Yeah. Yeah.
7,
Mhm.
8,
Yeah.
9,
Mhm.
and
10.
10.
Good. Now, your drawing as a human being is not nicely separated. It has some distribution, right? Distribution is when the math say that look, it's not nicely spread out. There's some clumping here, yeah, there's some clumping here, but that's all random. Once you do enough, you will see more of a neutral distribution. Okay. Okay, so that's 20 lah. So now then I will draw the nucleus law. So let's say I exaggerate the nucleus. The first nucleus is here, the second nucleus is here, and then the third nucleus is here. Okay, fourth and then fifth. Okay, so that should cover everything. Okay.
Okay. What now?
So most of you can say that when you kind of look at the average, most goes through kind of in the middle, in between the nucleus. Some will go very close, some, but most will not go very close because the nucleus itself is very big. Okay, and it's very small, very small. So these guys will kind of bend according to the graph. Will kind of bend around here, around there. Okay.
Which guys? Sorry.
The guys that go through kind of in the middle of nucleus will kind of bend some will bend some so to speak, will bend some, right? It will bend some. So those who bend some represent this part, represent this part. That's a significant bend, but not maximum. Who are the maximum bends? Very rarely, some crosses very closely to the nucleus. So you have like a lot of bend. So kind of this guy kind of represents this part, but those things are rare. Okay. Okay. So let's call this region 2, which is rare. Region 1, which is like normally that's just how most of them, most mean like maybe 50% will do that. Now how about region 3? Very simple. You have the second layer of nucleus. After you went through the first layer, your energy is already reduced, right? So the second layer will bend you even more and, so to speak, extract even more photon. But the photon will be less energy. That's what represented by region 3, the tail. So the tail drops. There's less and less energy to extract, so higher wavelength. But there's also less and less photon to extract from anyway. Because some terminate already, so to speak.
All right.
You have the third layer. The process keeps going because you have a lot of layer, and after a while, the electron will indeed run out of energy, and therefore you run out of photon to extract. So the tail kind of tapers out to represent that.
So for the number 1, it's the lowest
The
energy.
expected distance? No. How can number 1 be the lowest distance? I don't get it. This is kind of small enough wavelength, right? This is minimum wavelength, so maximum energy, correct?
Yeah.
This is kind of like in the middle wavelength, so kind of in the middle energy. Consider that the first extraction, just something like that. Consider it that way. The first extraction, the first major extraction.
Okay.
So you get your photon, the first major extraction. Some will terminate, but very little. And then after your first extraction, you'll get the second layer, third layer, fourth layer, and you'll taper out.
Oh.
Okay, that's the interaction between the super high-speed electron with the nucleus of the target.
So they bend within the metal, the electrons.
Not in between the metal. No.
Within.
In our eyes, it's basically striking the metal and disappear. But nanoscopically, we know that that's just vacuum with a lot of nucleus in between. This looks like solid to us. We're normal people. It looks solid to us, but to the electron, it looks like empty space with some nucleus here and there because the nucleuses are very small. So when the first layer happened, I'm going to have to erase all this. When the first layer happened, remember, they are already bending, remember. So they're already like bending a bit here, this one bending clearly like that, this one bending clearly like that. With the bend comes the extraction. With the bend comes the extraction.
The photon, yeah, okay.
Yeah, so when the bend happens, you have the extraction, like something like that, see? You'll just bend close to whatever nucleus is there, something like that. And then you go through the second layer, third layer, fourth layer for the further extraction. But, at that point, yeah. So this is what the chapter is trying to tell you. Okay.
Yeah, okay.
Right. So that's the continuous part. Right. So I have to explain the peak one, the K alpha and K beta. So please go down.
Scroll down. Okay.
Go down, yeah. Yeah, so alamak. So I just basically explain these two paragraphs. Okay, you can read it yourself.
Yeah.
Mm-hmm. Okay.
Different wavelength, different deflected, different matter when it pushing densities in different amounts of energy.
Therefore, continuous spectra.
Okay.
Therefore, continuous because they are slightly different from each other. There's slightly a bit different band, slightly a different distance, kind of. Okay.
Okay.
So moving on to the next page. So this thing doesn't explain the spike lah. Is basically what he's saying lah. Like the spike is not explained by this interaction, this Bremsstrahlung, right?
Okay.
So the spikes are explained by electron to electron.
Two electron.
Yeah. So remember when we talk about in the Jamboard, we're talking about the electron flying, right? Interacting with the nucleus, which is positive, right? Mm-hmm. But nucleuses have their own electron clouds. You learn this from chemistry. They repeat this in physics, but you learn this first in chemistry. And therefore, you have a complete atom. That's how you draw atom in general. They have their own electron clouds. Right. In chemistry, you learn further that the electron clouds are joined together, right, into a sea of electron. Blah, 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 blah. Whatever, a pi bond, lambda bond, alpha bond, overlap bond, whatever. That's the sea of electron. The sea of electron also is full of holes. I mean, the electron itself is very small. It's like we're drawing a solid thing here. It's not solid at all. The electron is flying around here, admittedly, right? So, what do you call it? Like our solar system. Like when we draw our solar system, we draw the sun here, right? And then we draw Earth like that, and then we draw, inside here, this is Mars, this is Venus, this is Mercurius. This is as if a solid orbit. It's not solid one. Correct?
Yeah.
What is happening is that like Mercury is here at one time, and then he'll go some orbit. Then Venus is here, and then like Earth is here, and then maybe Mars is here. Don't know where, right? And the electron flying in are basically like asteroids. Now, what is the chance of the electron hitting the sun or the Earth or the Mars? Very little.
Very low, yeah.
Very little. However, the asteroid is very likely going to be bent by the sun. Very likely. No hitting required. Just around there already enough to bend. Correct or not? That's the Bremsstrahlung law. That's the first part. The peak is explained by, now, compared to our solar system, the clouds are denser because there are more electrons flying around. And the electrons from each metal are combining to a single electron. So there are more electrons flying around. So the chances of the asteroid hitting one of the planets, which are the electron of the metal, are slightly higher. So they do exist because the clouds are denser. Okay. Through this dense cloud, if the electron hit an electron, if the electron hit the electron will, what happened when your electron hit the electron?
The electron hit, I mean, the collide, I mean.
They'll collide, and like ping pong ball, like the billiard ball, what will happen?
Heat, no? The transfer heat.
Transfer what?
Oh, no. They'll transfer, the transfer of photon.
Kinetic energy lah. No. They transfer kinetic energy. Right. So I'll just give you speed lah, right? I will lose speed, the electron flying will lose speed, and the electron in the orbit will gain speed, right?
Oh, I thought it was like exciting and de-exciting.
Precisely, that's what's happening. Exciting and de-exciting, because exciting means he go to higher orbit for a while, correct? Higher orbit, and then since it's not enough to knock him out, right? Knock him out means ionization, right? So this is not ionizing. This is exciting. He will de-excite back and re-emit the photon. Voila.
And that's what's being recorded into the graph.
The spike, and that is the spike. Because the spike is very precise, because that's what you will learn in chemistry and physics. The exciting, de-exciting, even in absorption and emission spectra, are very precise. It's not random anyhow one, like the break. The break is random lah. The excitation is not. Okay. So you have the spike law in very precise lambda, so to speak, representing the band gap lah, the gap between the first level and the second level.
So the lambda is of the energy of the
photon due to all these things.
Energy. So at this specific lambda.
Yep, the K beta.
This specific lambda.
That's another excitation, because you can excite, remember, you can excite to the second orbit, you can excite to the third orbit, remember?
So this is the number of photons released by the
excitation and de-excitation, right? This is the de-excitation. The de-excitation will release photon, correct?
They don't just release one, right?
Sorry, what? They don't just what?
They don't just release one photon.
They don't just what? Sorry?
They don't just release one photon.
The excitation and de-excitation, the de-excitation will release one photon for each collision. For each collision, each collision from electron with electron will excite the electron, right? So you excite one up and then go down and release one photon.
But why is it for this specific?
Yeah, because that's probably KB is probably the excitation from ground level, first level, right, to the third one, 1 to 3 lah. Why this specific one? You're probably thinking too much already. Why 61? Well, it depends on the metal. The point is each metal will have that excitation gap from 1 to 3, from 1 to 2, and it's very specific.
So this is the energy of photon released during the excitation.
The excitation from the third orbit to the ground orbit lah.
And the reason why the intensity is high here,
compared to the continuous spectrum, compared to the continuous spectrum, because it's easier for the electron flying in to collide with the clouds of electron, because there are more than the nucleus.
So there are more photons of
Chance.
this energy.
Yeah, there are more chance of
More
collision between electron and electron. Yes.
So there are more. That's why there are more photons of this energy being like
Yes. Therefore, the
emitted
peak.
compared to here.
Yes. Yes. Now, as for why K alpha is higher than K beta, because K alpha has a higher chance to occur because it's excitation from 1 to 2. That's more likely to occur than from 1 to 3. That's all.
Because why is 1 to 2?
Because 1 to 3 is a higher jump. So it must be a more ideal collision. It must be more head-on so that you can excite more, right? Remember, you can excite more. Whereas from 1 to 2, your collision doesn't have to be so perfect. It can collide, slightly less perfect. So the transfer is less, the energy transfer is less. So, but it's still enough for you to excite from 1 to 2.
All right.
Just easier to do 1 to 2 than to do 1 to 3. Even though both are collision. You have collision angles, basically.
Okay.
Right. And the continuous, again, is the representing the difficulty of hitting anything else, even the nucleus. But the nucleus will bend it either way, just like that. And the lambda minimum is probably the head-on collision with the nucleus, which is the sun, which is very rare.
Okay.
Right. So this kind of explains the whole feature of this graph. That's what they want you to understand. And the chapter almost ended already. Okay, kindly inspect your your X-ray chapter. I think it's almost done here. The continuous spectrum still same. So they're trying to explain all this, right? Explain all this. Just check it out. Check it out.
Peaks at characteristic wavelengths.
See, they're drawing the orbit, like the jump, right? See, K alpha jump from 1 to 2, K beta jump from 1 to 3. Voila.
K alpha jump from
ground level to second orbit, right? 1 to 2, right? Then K beta jump from ground level to third orbit.
Come from third first.
And then de-excite again, and then emit photon.
Yep. So the number of photons being emitted of that specific wavelength, which is from 1 to 3, is less
than from 1 to 2.
Because 1 to 2 occurs
more readily, more easily. But both definitely occur in greater frequency than the continuous spectrum, which is again not collision but from breaking.
Okay. So I'm still unsure of why 1 to 2 occurs more frequently.
Okay, first of all, the jump is lower. First thing first, you will notice that, right?
Okay.
The jump is lower. Therefore, the collision transfer of energy, right? When you collide, you will transfer energy. The collision, the energy transfer needed is less. Like imagine something like this. Actually, there are collisions even below 1 to 2. The 1 to 2 gap is quite high. You could imagine that, right? The 1 to 2 gap is quite high. So there will be glancing collision. You don't call that collision. You just call it, alamak, I'm glancing your car. Like, your car a bit bruised, my car a bit bruised, but we won't say that we collide. We may stop and argue. Alamak, you this, you break, whatever. But nobody's hurt. Right? Nobody's hurt.
All right.
But the jump from 1 to 2 is like the collision is quite serious. It's like I'm trying to avoid a pothole. Then I turn too much to the right, and then I whack your car. Right? I whack your car cannot transfer one lane, move to one lane. Luckily, there's no other car. That's a serious collision from 1 to 2. Right? You can imagine if I want to knock my neighbor car and transfer 2 lanes from 1 to 3. First of all, my initial knock must be of very high energy, right? Boom. Secondly, the knock must not be glancing. It must be a direct boom. And then he will move to the 2 lanes there, which is a very bad collision, but less likely to happen.
Okay.
So again, from 1 to 2 is just more likely to happen. From 1 to 3 is less likely to happen, but it does still happen.
Okay. Okay.
Right? And voila, we're done with Xray. Heisenberg is different already.
What even is this?
Now, what time is it?
7:50.
Goodness me, goodness, we have 15 minutes left, right? So after this, please remember to put in your question if there is, right? For the Xray, okay?
Yeah.
Okay, you're going to put it later because we don't have much time, right? So I promise you at this point, when you encounter the tutorial Xray, because that's what you want to focus on, the Xray tutorial, you'll find it quite easily understandable and there isn't much other variation. For example, this thing. This thing, you slowly do it, you'll be able to do it. Okay? Okay, that's the problem. So
cut off wavelength.
cut off. You can look at it. It's the lambda minimum.
Oh.
Why is there a lambda minimum? That's the question, no? Why is there a lambda minimum? Okay.
Okay, I need to look through it.
You will refer to your notes, but you will be able to understand your note and you will know where to look at it. Okay. Now I'll go to Heisenberg quickly. I think that is the this is going to finish, right? And then after that there will be the. We just flip forward. We just flip. Oh, yeah, definitely. Yeah. So for some reason the Heisenberg only half page, but yet you will need to use this. A bit annoying, huh? Now, could you please flip through first until this part finishes? I want to see the next set. That's
it. It's only 1 page.
Really? Finish? After this tutorial already? Like after this whole tutorial, there should be there should be more. There should be more after this. There you go. This thing, the nuclear physics.
Oh yeah, yeah, sure.
Now I will leave Heisenberg to you. It's not easy to understand. We'll talk about it during tutorial. So remember, you read Heisenberg, like what the heck is this? You go to tutorial and that's where you ask question and I'll talk about it later. Because they talk about Heisenberg out of the context. In the question, it's inside context, easier to explain. Okay? Okay. Right. So just know that Heisenberg has nothing to do with X-ray. I'm saying it like very loosely. It has nothing to do. And yet in the questions, you will encounter them. Okay.
All right.
Right. So now you have 2 options here. You can go to nuclear physics. I'll explain a bit more. Or you go to chemistry and I'll explain chemistry a bit more. Which one do you want?
Definitely.
Okay, go to chem quickly. Yeah, 15 minutes. Come on.
Well, it's either going to be nitrogen compounds or electrochemistry.
Choose. Quickly choose. You can choose the electro one if you want to. I'll leave nitrogen compound. We talked about it already, the nitrogen one.
Yeah, I guess we go electrochemistry.
Yeah, okay. So I'll leave the tutorial to you. Okay, we'll go to electrolysis quickly. Electrochemistry, right? So remember that in O level, they focus more on the electrolysis part. This one focuses more on the cell part. Now, what's the difference between electrolysis and cell?
I mean, the spontaneity.
Okay, electrolysis requires electrical energy and produces some kind of chemical reaction that is usually not allowable. So the input is electrical, the output is chemical.
Right.
When you do cell, it's your battery. Now you already learned the conversion of energy in battery from primary 5. What is the conversion of energy?
conversion of energy. I mean, just convert.
Yeah, from what to what?
Oh, chemical to electrical. I mean, that's
Voila.
obvious.
Voila, look, here, look. So basically, this chapter talks about battery. Look. Now, when we talk about battery, we really talk about the battery which is you're using inside your phone, inside your remote control, those batteries. Those batteries are what we're talking about here, so to speak. These are the basics of the battery. Look. Okay, that's the context. Any questions so far?
No.
Now, number one, electrochemical galvanic cell, that's the battery. Electrolytic cell is your electrolysis, the reverse law, number two law. That's the electrolysis. But they will focus a lot more on the battery side, which is part one. Never mind the fancy word like galvanic cell. Those are historical names. Basically battery lah. Common people will understand electrochemical cell as battery lah, something like that. Okay.
All right.
So moving on to the next page.
Some of this my teacher went through during lecture.
Why are we talking about, my goodness? So the oxidation number, we covered this, right?
Yeah,
During OChem.
this is revision. I think lecture went through this as well. I
Yeah,
feel like skip through this.
so yeah, it's very weird that they go through this, here, right? Okay, now electrode potential. Fancy word for, first thing first, how do you construct a battery lah? So how do you construct a battery? I'm going to explain how you construct a battery first. Please look at Jamboard page 2. You take one metal, M1. You take another metal, M2. Voila, you put it in electrolyte. Give me an electrolyte example.
H2SO4.
Good, which is you have H plus and SO4 2 minus flying around. Okay, good enough, potent enough electrolyte. Remember, the electrolyte is basically conductor but liquid. If you don't know why electrolyte is electrolyte, it's basically because I need a conductor, but it cannot be solid. Because certain things must flow very fast, and those certain things are not electron. I need things other than electron to move very fast. Okay, that's why an electrolyte is, for example, an acid or a salt. It's a good enough conductor.
The ions can do that.
Can flow very fast, right? Fast enough.
All right.
So in a cell, in a battery, you will connect it to, I don't know, something. If this is a battery, you connect it, for example, to a remote. Okay. Now this to construct a battery is as easy as this. Take two different metal, put it in a solution of liquid conductor, electrolyte, liquid conductor, electrolyte, and then you connect it, you close the circuit with something that needs the electricity, you will get the electricity. This simple. Okay. The electrode potential that your note is talking about now measures how good the battery is, meaning to say how powerful the battery is. Because different combination of metal will give you greater or lesser, so to speak, power, greater or lesser potential. The word potential here, you know this from physics, not from chemistry. What is the meaning of potential here?
Difference between the positive and negative.
No, in physics, the word potential means voltage.
I mean,
voltage.
Voltage.
EMF.
Oh, I thought it was more like, okay, never mind.
Yeah, the word potential here really means what the physics guy meant. I will generate a certain potential. Okay, volt. How many volt? So a more powerful battery will generate more voltage, let's just say that, and a less powerful combination will generate less voltage, sometimes useless. So even though there is voltage, it's not very useful. Okay.
All right.
So this chemistry chapter starts to talk about, okay, how are we going to measure the potential or the voltage? And therefore, we will know what combination works better, so to speak. Okay. Can you?
Okay.
Okay. So now look at this. You notice that there is only one metal, because they try to measure the electron potential, so to speak, one by one. So for some reason, they invent a method to say, okay, I'm going to just measure metal 1, and then metal 2 measure separately. And then when I put them together, I will have the total potential though. Keeping it simple. Okay. So we're going to measure each metal one by one, and the table that we construct will make sense with whatever combination of metal you do. Because if we measure the combination, for example, I want to measure copper with silver. And then I have to measure copper with gold. Then I have to measure copper with iron. And then suddenly I realize, hey, I also want to measure the combination between iron and silver. Oh my goodness, I have to measure so many things because I measure in combination. This chapter say, no, I don't want to do that. I just want to measure silver first, and then I just want to measure copper first, and then I just have to measure all the metal ones, and then I can combine whatever I want. Make sense?
Okay, makes sense.
Right? So now, how do we do that? That's what they're trying to explain. I'll go, because this is not supposed to be very complicated, and we don't have time. We have 3 minutes. Right?
I believe there was
Standard. Yes, standard. Thank you very much. Standard EMF. Thank you very much. Right? This is standard EMF. Now, no. This is where the combination happens. The potential of a cell or the EMF of a cell is the combination between the metal that is reduced and the metal that is oxidized. They call it half cell. The point is a battery needs 2 metal. That's the point. And you can just refer to the standard cell potential of each metal, which is in before this, and then just combine them. Right now, could you please flip to the, let's look at the standard, to measure the standard electrode potential of Cu, blah, 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 right? How do we do that? Now, look at this. The platinum electrode is used because the platinum electrode nothing will happen to the platinum electrode. It is inert. So the platinum electrode there to say that I am not going to do anything. I'm just going to conduct things for you, and I'm going to conduct things to the H+, to the hydrogen. So the standard electrode potential uses hydrogen as a reference. Everybody will be measured against hydrogen. The platinum is just there for conduction purposes. Right. So who is being measured here? The copper load. The copper will be reduced for some reason. Oh my goodness, I have to explain all the electrolysis again. How good are you in electrolysis back then in O level?
I was pretty good for a good 2 months, and then after that, I forgot.
Right. Okay. You don't need to know all that. What you need to know is if you set it up this way, this is a standard setup. Don't know why they set it up this way. Just like the X-ray or the photoelectric, they set it up because this is the best already, but you don't really know the history. Why do they set? Why salt bridge? Why? Let's say you don't know all that, but you need to know one thing. When they try to measure copper, they do it this way. When they try to measure silver, for example, what will they do?
I guess just put the silver there.
Change the copper. Well, strictly speaking, they'll change the copper to silver metal, but they will also change the CuSO4 to AgSO4.
AG, yeah.
Why? Because there's a possibility that it's the copper metal becoming positive, or the positive becoming the metal. Don't know which one. Either one can happen, so you must change both. Right? So that's why you must change the copper metal into silver metal, and you must change the CuSO4, which is Cu2 plus, into Ag plus. You must do both, so that you can just tell which one is which. Okay.
All right.
Right? And that's what we need to know. The setup is always the same. That means it's very standard. And the number is recorded plus 0.34 volt. How did we measure 0.34 volt? How did we do that? Physics. How do we measure a volt?
Positive,
How do you measure volt in physics? Come on.
Voltmeter, I guess.
Tara finished. Yes, so voltmeter.
Oh,
We just plugging the voltmeter there. Yeah. And then we get 0.34. Tara, standard electrode potential of Cu. Ta-ta-da, ta-da-da-da-da.
okay.
Okay. We have 0.34 positive. Don't know what that means. I can tell you something. Some metal will register negative value. I can tell you that.
Yeah.
And therefore, the flow of electron is reversed. So it'll be a negative, for example, negative 0.76, something like that. That will happen. Oh, there you go. The zinc. Look at the setup. The setup is exactly the same, but the zinc is being consumed.
Inside NSO4. Yeah.
Right? So that's negative, no? But the Cu is not consumed. The Cu is being added. Don't care. That's the result of the experiment. It will be always like that, and the negative and the positive value kind of represents that, so to speak. Represents that. Okay. All the complicated thing is happening here. It boils down to this number. Now let's flip. Let's flip and find the summary table, because in your data booklet, there you go. In your data booklet, which you need, flip it. Don't care about all this. Don't care about this. There you go. Okay, below there's the table, right? There's the table down here. No, okay, flip again, flip again, flip again, flip again. Ah, there you go, this table. This table will be in your data booklet in your exam. So you will be using this. All the explanation boils down to, I have done all this experiment. You just have to use it.
Right.
Okay.
Okay.
So, oh my goodness, there are positives, there are negatives. You don't need to memorize any one of them. You just have to know based on the question which number to pull.
Which one? Either whether they're reduced or they're oxidized.
You need to know that.
Or,
you need to know that. You need to know that. Okay. In this, you need to know whether, okay, in this question, is it going to be reduced or oxidized? You need to know that. Because the table is very specific. The table is, look at, for example, the table has a Fe2 plus 2 electron. Do you see that? It's minus 0.44 in the middle. Right. So this is saying that if the Fe ion is converted to Fe metal, it's going to be minus 0.44 volt. Let's say your question does not do that. Your question is converting the Fe metal to Fe ion. Can you use this number? Can or not? Can. Make it positive 0.44.
Oh.
Simple.
Oh, okay.
It boils down to as simple as that, because they do all the work for you. Okay.
Huh, okay. Yeah.
So if copper, you figure out this question and your question say, okay, the copper metal is being oxidized into copper ion. Which number will you be using? Copper metal to copper ion.
Negative 0.34.
Ta-da! Finish. Finish. Even though things are a little bit abstract, I want you to know that's what's happening in exam. Like that's what's happening in a question. That's what's happening in a tutorial. You just refer to the table, but you have to think through first what reaction is happening here. That's the thinking part. The table won't tell you. The table just tells you the number.
All right.
Okay, right. So let's flip. Now you have the table. The table is a summary of what we just studied, the standard electrode potential. Work example 5. Use relevant data and data book, blah, 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 to decide whether this reaction will proceed spontaneously. Okay. Well, what do? They give you the reaction. You notice the reaction they give you, correct? So where does the question stop? The question stops when the reaction is given. You have to work out the rest. So what do he work out? Oh, he works out that, oh my goodness, in the booklet, you do have I2 to I minus. Please refer to the booklet. Does the booklet contain this? I2 to I minus. Positive 0.54, correct? Simple, right? But what other reaction might you need? Fe, but in the origin is to Fe3 plus. You need that. Does the booklet give you Fe2 plus to Fe3 plus?
Fe2 plus. Yeah, there you go.
No. The booklet gives you Fe3 plus to Fe2 plus. So that's why it's,
Okay.
yeah. So the booklet gives you Fe3 plus to Fe2 plus, but you need Fe2 plus to Fe3 plus.
I thought here was Fe3 plus, right?
Look
Oh,
at
no,
the
here's
reaction.
Oh,
Yes.
2 plus 3 plus.
Correct.
So 2 plus 3 plus is
Minus 0.
negative 0.77.
Correct. Now look at the working. He will take positive 0.54. Never mind the number minus. Don't care. Don't care. It's going to be positive 0.54 and negative 0.77. Which is going to be a negative number. Like I said, never mind the negative and the positive. If you can understand that from your teacher, good for you. To me, it's very simple. It's positive 0.54, negative 0.77, and negative 0.23. Done. Never mind the formula. Just flip the negative. Just flip the positive 0.77.
So it's just plus?
The table is plus, but you need the reverse.
So like when you're doing this conclusion, just add them together.
Yeah, correct. Because that's the true reaction which is happening.
Okay.
The other half is positive 0.54. The other half is minus 0.77. What's the use of all this? Oh, wait a minute. The voltage is negative. Oh my goodness. This reaction requires external voltage. That's the meaning. This reaction does not happen unless I provide additional voltage from outside. That means this reaction requires a battery to push things. That's a good conclusion. So I will not be able to have this reaction. But another conclusion will be if I reverse the reaction, it will be spontaneous. Simple. If I go from right to left, then it's positive 0.23. Then that can happen without a battery. In fact, that becomes a battery.
Okay.
Right? So this is already a good example of what this chapter is about. Right? In lecture practice 5, that's exactly what's going to happen. You do that by yourself. Right. And the rest of the chapter will just simply be something like this. This is the basics already.
All right.
Please do this at least once. Please do this at once. And then the other reaction, just figure out the two reaction immediately, right?
So it's negative 0.54.
Right. But the number matters, okay? It's 6 and 3, okay? The number matters.
Really, I thought they said it was like independent of, right? They just say it was like independent of school.
Oh my goodness. I did something wrong with it. Please follow this question. So please follow this note. Sorry.
All right.
Right. So you have that. You write down the number immediately, right? Positive or negative. Right. And then the other reaction will be
CR207. So CR2 is negative 14, negative 12 plus 6. Plus 6
okay.
plus 3.
Don't think that's what they will give you, but okay. Let's take a look.
Okay, it's not here. Maybe it's in the entire thing. Give a second.
Yeah, check out the entire thing. The entire is much longer than this. All right. There you go. Yep, good.
There you go.
The exact thing that you need. In fact, together with the H plus and H2O. Very convenient, isn't it?
Yeah, 1.33. Why? Right. But why is H plus there?
You look at your original reaction, please. Okay, original reaction in the question. Voila, it's conveniently there.
All right.
Right. So those four things lah, boom, positive 1.4, and then your conclusion will be this is probably spontaneous lah. Okay. Now you just do that. No, enough. The math is very easy. No need to press. The reaction is spontaneous, right? It's obvious lah.
Yep.
Okay. Right. So I'll leave that to you to figure out the rest of the chapter. Right.
All right.
So our agreement right now is you're gonna ignore the photoelectric. You're gonna ignore the spectrum for a while. You're gonna jump right into X-ray for physics lah.
Actually, 1.44 minus 0.54 is not 0.79.
Actually, it's 1.33. If my eyes didn't fool me just now at the table.
Oh, was it? Yes, it was.
Hello. Try again. See whether it works or not.
.133. Yes, it is. Yeah. Okay.
Right. Okay. As promised, well, this question at least, it is not very difficult to understand for now. It is not.
Right.
Not meant to be complicated. Now you will see the complicated question. It ain't much lah. It ain't much. I suppose that's the good news. You just have to figure it out. Okay. Now here's the agreement. You're gonna ignore the physics chapter before X-ray lah, but you concentrate the tutorial on X-ray and try to figure out the Heisenberg. That's the minimum lah. Okay. So we'll start our catching up like this. I'll continue helping you with the nuclear physics on Tuesday, hopefully, so that you almost caught up by leaving 2 chapters behind, basically.
Yeah.
Right. Now for physics, for chemistry, you are not too behind, right? You're not too behind, right? You're not really. Am I correct?
Not really. So
you can probably study the lecture already, and you can probably do the tutorial when you need to lah. But focus on the nitrogen one first, because your teacher say they will discuss that.
Yeah.
So you don't notice that I kind of skip the first part. I kind of like gloss through it because it adds complication that you don't necessarily need lah. You understand the context first. This is the context. This is what they want. Easier to understand. Okay, so when you do the tutorial, you find out whether the first few pages are how necessary they are, so to speak. Then you would have, I predict you will caught up quite easily because the chapter is not much. It's not much.
Okay.
Okay, any other question?
No, don't think so.
See you on Tuesday then.
Okay.
All right, bye.
Bye.